Let's look at an example of a second-order differential equation and find solutions to y double prime minus y equals 0. Since we don't have any techniques for solving such a differential equation, can we guess solutions based on our knowledge of derivatives? Rewriting this as y double prime equals y by adding y to both sides may help figure it out. We're looking for a function that if we take its derivative twice, we get the original function back. The easiest solution to see is y equals e to the t, because the first derivative of e to the t is again e to the t, which has the second derivative e to the t. So e to the t satisfies that its second derivative is equal to itself. Are there any other functions that work? Another function that works is y equals e to the negative t, because the first derivative is negative e to the negative t, while the second derivative is the negative of that, e to the negative t again. So y equals e to the negative t also satisfies y double prime is equal to y. And are there any more? We may notice that constant multiples of these are solutions as well. For example, y equals e to the 3t or e to the 5t, or any constant c1 times e to the t will work, and any constant multiple c2 times e to the negative t will work. The reason for this is we can bring the constant outside of the derivative. So the second derivative of c1 e to the t is again c1 e to the t, which is what it means to be a solution to this differential equation. And similarly, due to the linearity of derivatives, if we have two solutions, y1 and y2, then their sum, y1 plus y2, is also a solution. And combining these two ideas, we can conclude that all functions of the form c1 e to the t plus c2 e to the negative t, where c1 and c2 are constants, are also solutions to the differential equation. Now let's use what we found out from this example to find solutions to differential equations of the form a times y double prime plus b times y prime plus c times y is equal to 0. We will look for solutions of the form y equals e to the rt for some value r. Just as we saw y equals e to the 1t and y equals e to the negative 1t were solutions in the last example. For y equals e to the rt to be a solution, it must satisfy the differential equation. And to test if it does, we'll insert y prime, which is r e to the rt, and y double prime, which is r squared e to the rt, into that differential equation, which gives a times y double prime, which is a times r squared e to the rt, plus b times y prime, which is b times r e to the rt, plus c times y, which is c times e to the rt, all equal to 0. Now, when we're trying to solve an equation equal to 0, it's always helpful to factor. And here, we can factor out e to the rt, giving us e to the rt times the polynomial a times r squared plus b times r plus c is equal to 0. And the reason that factoring is helpful is because now we have two numbers multiplied together, e to the rt, and the polynomial a times r squared plus b times r plus c, to get 0. And if we multiply two numbers together to get 0, one or the other must be 0. But the exponential e to the rt is never 0. So we can conclude that for y equals e to the rt to be a solution, then ar squared plus br plus c must be 0. And this is very powerful because it allows us to find solutions to that original differential equation by simply solving a quadratic equation. This quadratic equation, which plays such an important role, is called the characteristic equation. Also note that because of how the characteristic equation is constructed, its coefficients are the same as the coefficients of the original differential equation. so we can immediately go from the differential equation to its characteristic equation. We'll see this in the next example.